Hello, and welcome to SNEA SDC. I'm Rohit Srivastav. I'm working as a technical director at CalSoft. During my 25 years of professional journey, spent nearly 15 years as a storage engineer and storage performance engineer. Today, we will talk about computational storage. In fact, we will take a we'll take a step back and look into the changes what happened in the storage industry, which eventually led to this computational storage. So let's start our discussion with a little peek into the past and how storage industry transformed since magnetic disk. But before that, let's look at the agenda of this today's discussion. We will take a short recap into the evolution of storage industry. We'll trace a journey of computational storage, look into the business angle, a few of use cases, and conclude upon it. So let's start with the recap, a short video, what we have prepared, highlighting the journey into, or rather the changes into the storage industry since the advent of magnetic disks. Interesting. That was a good insight into the past, how storage industry evolved. And the biggest disruptor in the storage industry was the advent of flash storage. So, and this reminds me of a very interesting discussion I had when I started my career as a performance engineer. I was having a discussion with my mentor and my supervisor, and his question was, "How do you see flash storage um, onto within the storage industry?" And my answer was, "Flash storage is fast. Flash storage is not the challenge. The challenge is the interconnect of the flash storage." Uh, and at that time, my only experience with the flash storage was with the cameras, one which I had supported CFI, the other one which was supporting SSD or SD card. So yeah, so sorry, I jumped a slide ahead. But let's look at the objectives with which storage industry moved forward all along. And the objectives were, maintaining availability, that the data is available to mission critical or business critical applications all around. Even it should be capable, the system should be capable of tolerating hardware failures, manageability, uh, the ability to provision and reprovision storage, maintaining backup, and having those storage offloading like storage services like snapshotting, and so just to enable point in time backups. Performance, yeah, since I hail from performance background, this is of real interest to me. And one of the prime motives of the entire storage industry had always been how to enhance, how to optimize the overall system performance, including that of applications. And and the reason was primarily because compute, they were doubling the speed, doubling their capabilities at every 2 years, and so was memory. But storage, on the other hand, it was lagging behind. And more often than not, it was a storage which was becoming a bottleneck for most of the applications when they were benchmarked on their performance aspects. So yes, what can we do to enhance performance of the storage, performance of, application performance, and the answer lied how to improve upon the IO performance, that's the storage performance. Scalability, well, data had been growing, and it has been growing at a tremendous pace, and the ability of data centers to be able to match up that with that growing demands, and try to reuse or try to exploit their existing storage hardware to their maximum utilization. And the next one was security, how to prevent data loss or data theft. Data loss was again achieved by disaster recovery solutions and backup solutions and whatnot. Data theft has caught upon the storage world within last, say, about 5 or 7 years, primarily because with this whole um, regulations and compliance which are coming into the play. And all through along all these 5 aspects of the storage industry, one thing which remained constant was the cost option. And yes, keeping the cost low was one of the other targets of the storage industry. So we looked at what were the driving factors for the storage industry. Look at this. Let's look at the storage timelines in terms of storage topologies. So from a storage topology perspective, the simplest and the first one, or rather the easiest, was the direct attached storage. Here the disks were plugged in into the server directly, and to achieve a fair degree of all those 5 objectives, there were a few solutions which were implemented here, primarily like RAID and file system and caching. They tried to improve the performance, and they tried to improve the resiliency through RAID, but that could only address to so much in terms like a single drive or 2 drive failure can be handled through RAID. But all of this that came at a cost because the system resources were getting utilized. There are servers today which have their own dedicated RAID controllers, and these RAID controllers can offload RAID functionality like RAID 1, RAID 3, and RAID 5 functionalities, delivering both on terms of power and resiliency, uh, 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 and performance. But that's a little what, to that extent what can be done over there. However, on the availability front, there was always a challenge in case of a server failure. data can be lost. Data can get lost. The next one was offloading this whole storage services, RAID functionalities onto a different box and connecting the box to the server, leveraging fiber channel interconnect, a low latency and a high bandwidth interconnect. This actually proved very well because it addressed more or less almost all the objectives. It matched, it addressed all the objectives of the storage world. The only challenge here was the cost involved. The cost was high because this fiber channel network, the SAN network, is expensive, both in terms of setting it up and also maintaining in going forward. So yes, all objectives were met, but at a relatively higher cost, or rather much higher cost. And then the next type of topology which came up was NAS, which addressed more or less all the objectives. Now, there was a little trade-off done over here because it employed the existing Ethernet, or it also went ahead and tried to exploit the same copper infrastructure available in the data center, and trying to implement fast Ethernet over it. And so almost all aspects, all the availability, manageability, performance, scalability, and security, they all were met over here, and at relatively at a lower cost. But there were some trade-offs done when it came to in terms of the performance. So yeah, so there was a slight trade-off here. Nonetheless, it met more or less a majority of demands which were posed upon from the storage world. And these three different topologies, then there was this whole notion of how to aggregate heterogeneous storage, which is available within the data center, and how to present a consolidated view, a consolidated management mechanism, and so on. So they came up with this software-defined storage, which was again an API controlled, policy-driven storage subsystem. Here, different types of storage were connected to one, or rather accumulated together and presented as a unified view to the applications or servers which were requiring storage services. There was a little bit of caching also available in order to improve upon the performance. And again, since it's a policy-driven and policy-governed storage, so it can be configured through software what kind of IOs are going to land onto what type of storage, and so on. So this is a good solution for this is a good solution which is prevalent in the industry. The next big change which happened in the storage industry was the advent of object storage. Remember, so far we had been dealing all in block and files. And now suddenly we move away from this whole notion of block and files, and rather we start dealing in blobs, the binary data and metadata thereof. What it provided was it provided infinite scalability. It also provided a very fast retrieval. Remember, we are moving away from hierarchical notion of data storage, that's from directories and files and so on. Instead, everything is now stored in a flat structure. The only thing what is required is metadata and its corresponding data. So the retrieval is faster. It's like almost everything can be retrieved in the same amount of time. So there is no traversal involved, and it certainly is at a much lower cost because all of these was implemented on commodity hardware. So object storage, as I say, like it was the next big change, next big thing in the industry. So this was all about this storage from the devices and the topologies and different concepts which came into the storage. Now, let's look at what actually led us to this whole computational storage. So if we look at this whole a typical compute system or a typical system over here, then there is a CPU and storage, and let's take SSD as a conventional storage today. So here, if CPU has to process data, it will read data, it will fetch data from the SSD, and it will process and eventually store on it. So what happens is there is a lot of data moving back and forth between the CPU and the storage. With this, if I look at the past, if you recall from the video, we had this challenge of interconnects, and we had this challenge of several layers of I/O processing within the operating system and all that, and we tried to bypass with a mechanism like SPDK, where with the implementation of these storage drivers in user land, and trying to bypass the entire operating system altogether. So now what happens is, because we have all those things in place, and because the data is being shuffled between the storage and CPU so much that this data travel time, that starts becoming significant. And this is where the performance bottleneck starts appearing. So this becomes a hotspot. Now, how to deal with it? One solution is we place a compute which is very near to the storage, and we define those services, the storage services which are required as APIs on the compute. So now CPU only makes API calls to the compute, and the compute does all the pre-processing and processing. That's fetching data from the storage and processing it and moving it back, and only the result set is forwarded onto the CPU. Analogy to this could be something similar, like if I take a case of SQL-aware storage. So I have an edge node, I fire my complex SQL query onto the edge node, and then this edge node, what it does, it breaks down this complex query or whatever data is required into its subqueries and forwards it to the nodes where those tables are residing. And then those nodes, they do this whole pre-processing, or rather processing on those SQL queries, and only the result set is forwarded onto the edge node. Now, edge node combines those result set and puts, applies all the constraints which are there on the subqueries, and eventually passes on the result to the user. So this way, what happens is that the traffic on the wire gets minimized. But still, if you see, there is a lot of shuffle between the compute and the storage. However, the problem of data being traveling between the CPU to the storage and back and forth, that had been addressed to a lot larger extent. So next, what they did is they bring the compute inside the storage, so that I mean the compute is residing on within the SSD. So we have this within SSD we have something called a controller. So the compute now resides inside the controller itself, or side by side. And the API definitions, now everything gets moved into the compute only. So now all the data which is going to shuffle between the storage and the compute, it's within the same form factor. That's the typical 2.5-inch SATA form enclosure as defined. So what we have done is now we have almost eliminated the shuffle of data between the compute and the storage, and it is only limited within it's the whole shuffle happens within the same storage controller itself. And this is the fastest way what we can go to. And this is what is a computational storage. So we have a storage and we have a compute where computational storage services reside. And the CPU only makes call to these storage services. And the data pre-processing and processing happens on the compute, and the result sets are forwarded to the CPU. What it helps is, it has, again, as you see, that it has almost eliminated a major chunk of data movement on the wire. And now it has freed up the bandwidth which is required between the storage and the CPU. It has reduced IO traffic again. And the most beautiful aspect is this whole form factor typically has a power footprint of around 20 watts. So it is very easily and massively scalable. Now, having defined this computational storage, where we try to put compute within the storage, the next topic would be, what are different types of computational storage? And the answer is, there are primarily two types of the computational storage. One is the fixed CSD, as we define as FCSS. Here, what we have is, we will have an SSD, we will have a network IO, and network or IO, and we will have an FPGA. This FPGA is primarily used for development, and users, or rather manufacturers, they have a choice when this the entire logic is implemented on FPGA, they can switch from FPGA onto ASIC. So primarily what it offers is it offers little to none flexibility as far as programming is concerned. And these are targeted for very specific use cases. A typical use case could be like data deduplication, inline data deduplication, where we have, we define certain logic and certain memory which is residing inside the FPGA, and leverage that and try to implement that. Or something like vectorization of image, or inline data compression, or something like inline data encryption. So there are fixed use cases, fixed and very specific use cases for which these fixed CSDs are used for. The next one is the fully programmable CSD, where we have options of having CPU, GPU, TPU, tensor processing unit, and FPGA as well. I mean, it could be it could be a mix of all this, or it could be all, or it could be a mix of all this. I mean, depending uh, upon the manufacturer and depending upon the requirement. There will be a network I/O. There is a, a sizable amount of RAM also available present here. And we have a SSD. Typically, these SSDs are they could go from anything from like 1 TB to 2 TB or 3 TB. I mean, it depends. Yeah, and because we have CPU, GPU, number crunching, tensor processing, AI, and FPGA, some smart logic or custom defined logic, which we can program over there. So it's a very flexible device. Now let's look at the business side of it. And when I say business side, what I essentially mean is me as an engineer, I'll try to see what is in there for me. As a performance engineer, I know data is the king, and it is, the important aspect is to make that data available where it is required within least amount of time and consuming least amount of resources. So, so the question is, I have an application and I have a set of data. How do I make that data available to the application? And this is where these CSDs, they come into play, because now the application or a part of that application can be built on the compute which is available within the storage itself. How it helps? It helps again that the amount of data which is need to be transferred, it just minimizes it, because the amount of data is minimized, so it cuts down the latency. Because less and less data is going on the wire, so it improves our security and privacy concern. And again, since it is having a very short power footprint, so it helps on the power consumption side as well. So these are the benefits which I can take as a performance engineer, and I will try to start designing my applications on the computational storage, leveraging computational storage. Now, talking about the businesses, the organizations, from the organization perspective, okay, how does it help them? There is an IDC report which says that nearly 30% of world's data will need real-time processing by 2025. Data is, right now, the amount of data which is getting generated, it's humongous. And it's only growing. And to process that data in real time or near real time, that would require an infrastructure which is capable of handling that. And this is where, again, computational storage will fit in there, not because one single computational storage can achieve that, but it's a parallel system. It's an array of computational storage which can provide that amount of storage and that amount of parallel processing to achieve overall real-time processing. Now, again, since these computational storage devices, they have a form factor of 2.5-inch SATA drive. So because of this, and these are completely standalone systems, if I were to draw an analogy, in a big data system, one computational storage device, I can treat it as one single node. So because of the form factor and because of the power requirement, it gives me a flexibility not only to restrict its application within the data center, but also to move it beyond data center. And that becomes a very lucrative deployment in IoTs or edge nodes. And again, if we have something like inline encryption and inline decryption logics built into it, then again, a security posture can also be improved. So this is how computational storage addresses the requirement on the organizational and business side. Let's look at the few use cases. Before we jump into the use cases, let's try to see what type of applications or where computational storage fit. In a nutshell, wherever there is a huge amount of data and it requires and that requires a processing which involves a lot of data to be shuffled or moved from within compute and storage, that's where computational storage fits in. Applications are numerous: IoT, ML, edge computing, and whatnot. And the benefits are also tremendous again, because and the most lucrative benefit of what I see from the computational storage side is their requirement of low power footprint. The first use case which I wanted to talk about is let's look at Ceph. Talking about Ceph, people familiar with Ceph, they know that the bottommost layer of Ceph system is the object storage devices. Now, these object storage devices can be replaced with computational storage devices. And so we have a flexibility of low power, relatively low cost nodes and an array of them. And we can offload all the Ceph daemons onto the CSDs and eventually build a distributed Ceph system on top of CSDs itself. And this would and this system has a capability of competing with conventional storage systems. Not that Ceph did not have, but with this system, it has a potential to compete with the tier 1 storage as well. In the next use case, let's talk a case of real-time processing. Now, in real-time image processing, we have a camera, we have a server, and now the challenge is if I try to take the raw image from the camera and move it to the server for processing, I will never be able to achieve it in the real time because raw image itself is big and the bandwidth required will be high. And think of a system where we have multiple such cameras and we need a real-time processing. Solution is we can have FCSS and FCSS where the FPGA or there could be an ASIC whose job is just to vectorize the images which the camera is capturing, and then these vectors data can be stored and shared for further processing. We can leverage, instead of FCSS, we can also leverage it to a programmable version also, where we can do processing on the storage device itself. and the industry which where it can be fit in are numerous, right from X-ray, insurance, healthcare, or automotive, or even traffic control systems as well, where real-time license plates recognition can be achieved. CDNs are again an interesting way, because the whole objective of CDN is to manage the content delivery to the end user, which is geographically segregated and sparsely located with respect to the main server or web services provider. There are open platform edge services, very well defined open platform edge services. And what we can do here is that we can replace those PCSS, programmable computational storage devices. We can replace the edge nodes with programmable computational storage devices, and have those devices running the OPES applications. Furthermore, with this leveraging AI and ML, what we can do is we can train them for intelligent real-time routing decision and intelligent content management. So these are the few use cases of computational devices, computational storage devices. The limit is endless. I'm just capturing a few of these just to give a food for thought, trying to see, I mean, for us to explore where all we can fit these devices, and we can leverage upon them. So as to conclude here, there are a few key takeaways. One is, again, since NVMe, see, for the flashes, the biggest thing was NVMe, and the next best thing to NVMe is computational storage. That's how I see. There are numerous use cases and numerous applications where computational storage devices can find themselves helping out the real world problems. Again, as we talked about IDC, that almost like about 30% of world data will be requiring a real-time processing by 2025. And so computational storage again becomes imperative for us to be there. Computational storage, because of the low footprint, both in terms of form as well as power, they are really helping us out for scaled out solution. And SNIA has been doing a great job of the working committee on CSD and standards is really accelerating CSD's adoption towards real life use cases. Now about CalSoft, yeah, we are a 22-year-old company specializing in product services delivery. We deal with digital services, cloud and security services, sustaining support, DevOps, UI, UX, IoT, AI, ML, and platform solutions. Our expertise or technical expertise spans across storage, cloud storage, software-defined storage, hyperconverged infrastructure, data protection, data deduplication. And we do have our offerings, our IP offerings in form of storage accelerators, Windows CBT, iSCSI test suites, Office 365 backup solutions, generic cloud solutions, and emulators. Here are a few links for references. And with this, we come to an end to this discussion and talk. Thank you very much.